what Norm asked me to do is kind of give you a look forward to the stuff's happening. One of the advantages, like many of you that you heard this morning of being a global company, is we see things that are happening around the globe, and tied to that, we see how these things are going to converge. And the convergence doesn't necessarily come from an individual market. It comes from all the markets. It comes from manufacturing. It comes from media and entertainment. It comes from architecture, engineering. These things tend to bleed. And so really what I want to do is kind of give you the talk around the future of making things, which is really about, you know, as we think about this, and George mentioned it earlier, you know, we need to understand what our environment is before we figure out what we can do differently with it. So that's why I call this creating the digital mirror of the physical world, because that's really what we're trying to do. Our physical world, this is probably the best definition I've seen in a long time, and it comes from a financier. You know, the role of technology is really central to making sure that infrastructure investment has something to do with how we want our cities to behave, how we want them to grow, how they want to innovate, and really address the world of future demands. I mean, that summarizes pretty much everything that we've seen here. That's the goal of a lot of what's happening with the Blueprint 2025. That's what we'll get into, but that's really what we are after. You know, we talked about this earlier. It's not so much the investment, but here's the top 32 countries in the world. They are responsible for $218 trillion in infrastructure assets, right? That's with a T. And as you know, no country is immune to the fact that these things will have to be changed, right? Somehow we have to add to them, remove from them, convert them to a different use, but that's a big order. And just the U.S. alone, as you know, is we got about $1.6 trillion. We got to figure out how to do that. The challenge we have is unlike when you buy an automobile, there is no Kelly Blue Book for infrastructure. You can't say, well, this car is 2 years old, but it's got 400,000 miles on it. And conversely, you can't say, well, that's a 50-year-old car, and it's going to get 5,000 miles on it, and here's the value, and here's how long it's going to last. We don't have that. Wish we did. So everything tends to be a gamble. And what we want to do is really start thinking about it. And I think George kicked it off earlier. There's a reason why we need these models in real time, is we have to be able to get an up-to-date assessment of how all this stuff works. And 10 years ago, we couldn't do that. But now with the power of cloud computing, the types of reality capture tools, the ability for large-scale modeling, we can do this. And there's a big gap between the standard of capability of tools today and the standard of practice. And you'll see some of that, because I'm going to show you some examples of what this means. So the whole point about this is, how do we unlock infrastructure's potential? When you see a site like that, and that's not a photograph, that's a 3D digital model, by the way, that took about an hour. And it's accurate to about 6 inches, and you can get a lot deeper there. We now have, what do we want to do with this? What can we do to that site? What can we do with that road? What can we do with that bridge? And you start to see this, the whole idea around the Blueprint 2025 is do things differently, to try to understand what do we have, how quickly can we ask, because the technology can support these decisions. But, you know, we have a challenge of these things like contracts, which are different than construction. You know, contracting is not construction, even though they're tied together. So here's a couple examples. Here's one of the most visited sites in the U.S. This is the U.S. the U.S. Air Force Chapel at Colorado Springs. This is a fully rendered digital model of everything inside and out. Why? Because the roof leaks. That's bad, right? You know, and the ability is this can be captured very rapidly, and you know what's going on? We're running high-end analytics on it for heat loss. We were looking at it from retrofitting things that didn't exist when that was built, but keeping the integrity of what that is. And that is down to millimeters, right? So the idea is we can get very accurate representations of the things we're looking at, and here's a perfect rendering of the inside of that, right? Very historic, very high profile, but like anything, it still needs to have it updated. And this can be played out over and over again. Our friends from the Netherlands, if they haven't left, here's the perfect, another reason why we need these type of models. This is a local development, a new era of localism where the city is using this model, and the people that will live within the view here are using this to crowdsource their own infrastructure problem. right? They are contributing to what they want that greenway to look like, where they want the parks, where they want the roads redone. And guess what? They'll pay for it in their little neighborhood. Why? Because they understand what's happening. That model is tied to costing. They understand the expense of a decision to put something here versus something there, and they're willing to sign up for it. Now, granted, it's the Netherlands, and it's a small city in the Netherlands, but the idea is when we start doing these types of things, the crowdfunding comes out because people are contributing to this higher picture of what they want their future cities to look like. And we're mentioning drones. John mentioned drones. I've done a lot with drones. It's cool. You can do really cool stuff with it. The power here is that you have, at the first time, the ability to, on demand, create very highly accurate sets of information for all existing conditions, internal and external, whether it's scanning or whether it's out. And I'll give you an example. I want you to look at that for those that are in the eye chart. That little thing means is that this entire thing I'm about to show you is accurate to within 6 millimeters. And this is a 6-acre site. It took a day and a half to survey the buildings inside, outside the building, and then register all that information and get a 6-acre site model that's within 6 millimeters. Right? Now, I don't expect you to do that to the scale of New York City or Chicago, New York, or Amsterdam, but the point being, it can be done very easily now. Because with cloud computing, you can put these massive sets of information and have it generate this thing in real time. So the question is now is, okay, now we have it. Now we can figure out kind of what do we want to do with this digital mirror? Where do we want to change? What do we want to do it? And this was a proof of concept, but the idea being is that we have the capability, the standard capability technology versus what we don't have. And of course, when you look at some small 6-acre site, and then we start scaling it up to other things we have to really deal with. Population, trying to figure out how do we increase our transportation capacity. It's not like we're going to double that deck anytime soon. And dealing with everything from how do we deal with impact events, stressor events, and then of course, how do we work when we have projects that are all over the globe at different phases and use that level of expertise because everybody's got certain expertise that sits around the globe. More fun to go. So really what we're starting to see is a massive amount of disruptions, and they're coming in kind of 3 areas. There's the changes in production, in other words, how we think about what we're going to produce and then how we execute it. Tied to that is answering the demand. The public is changing what they want. Anybody got teenagers, you'll know that they would rather not have a car, they'd rather have higher bandwidth, right? Because they'd rather talk to their friends than drive around, or they can Uber if they need to, right? So it's going to change configuration of cities, it's going to change the demand that we put on these things, and as you had Cora say, with those 50 billion devices come 50 billion entry points into screwing it up. So we have to think about how we do that. And that changes what the products are, in other words, what we eventually deliver. But we have the ability to use this power. So here's state-of-the-art intellectual production. And we were talking about underground utilities. Once you have that information, you can do some very cool things with it. This is a map of the city of Los Angeles. It's very accurate. It can show above ground, below ground, and when you start thinking about neighborhood impact, district impact, city impact, and oh, by the way, this high-speed rail thing, right? You now can put entire projects and cities in context, so you can scale from the city and just keep backing out and eventually see where the high-speed rail is going to come through and go up with the same model. All right, this is one model. This is not a dozen models. Of course, you're not going to run this on a laptop, but the point being we have the computing horsepower to make all this stuff happen, so we can start looking at the interplay between this project down the street, this one out in the neighborhood, and how these things are going to be synergistic or not. And this one about fabrication. Somebody mentioned about the advantages of China. Well, one of the things is they can automate stuff better than we can. This is a 30-story building put up in 15 days. I'm going to have our friends over there in the video trying to walk it back after it's done because it's fast. Can you just back that slide up once? Right? You can count the clocks. It's 15 days. They are able to, let's back it up one more. Okay, there we go. Take and put together this building because everything's prefabricated, and building is totally green. It's LEED platinum. It was move-in ready after it was done. It can withstand a 9-factor earthquake. It's got an extensive air handling system, 15 days. Now, going back to the combination, we were earlier talking about being able to do things like, well, let's get the contract, and what's that RFI? There is zero change orders here. There's no RFIs, all right? This same company is planning to do a 1 kilometer tall building in 150 days next year, right? Just times 10. The point being is that it's less about the methods we do to construct, and our biggest challenge is getting out our own way when we do contracts and procurement and everything else, right? Imagine what we can do when we start building bridges that way and the rest of the buildings, how quickly we could upgrade and turn over infrastructure if we can get the procedures out of the way to make it happen, right? That's the standard of a capability of technology, right? We can model things, we can prefabricate them, and then construction is not construction, it's assembly. And you can see the results of that. And so when we start thinking about demand, whether it's autonomous cars or figuring out how to take a power plant that's in a dam like that and swap out that turbine because, hey, guess what? It's been 10 years and GE invented a new one that can operate and generate 3 times electricity for the same size of water, amount of water. How do you replace it, right? Thinking about modularity and designing these things so you can swap these things out like batteries. These are the types of things that we've got to start putting in so you're planning for the maintenance of it directly, but in a little bit different way. Because, you know, when we start thinking about these projects, it's really a combination of technology and whatever cool idea we can think up. So here's just another example of how rapidly you can capture up-to-date asset information. This is the Rio Tinto mine in California. Everything that gets hauled out of there, the big trucks that are the size of half of this auditorium, all are autonomous. The excavators are autonomous. But guess what? Autonomous cars can't see ditches and other stuff, right? So when it rains and other stuff happens, that's bad. And you're not going to be throwing surveyors out there. They fly this with drones every day or every other day. They capture that information, they model it, insert it to the new model, upload that up, and then now the trucks have an up-to-date model every other day. It covers their quantities, it covers their vehicular play. You can lay out roads real quickly, change it, right? It's possible. You know, this is real project stuff. This is, you know, kind of the vaporware. This is in Hollywood. These are actual customers. This is what they do. This is the speed at which we can do things to tackle some of our infrastructure problems. Because the biggest problem we're going to have, and we started touching on it, and we'll certainly touch on it more on the panel this afternoon that I'm moderating around the Internet of Things, is the products and their seamlessness between what is hardware, what is software, and what is a physical asset is rapidly changing. Every single thing has an IT component in it somehow. They're going to start talking to each other. You know, putting the sensors in is not that big a stretch. It's what happens when the sensors in the water pipe start talking to the sensors in the road. Say, guess what, I broke. You better throw something else because I'm going to wash out the water underneath you. That's when it gets interesting, right? When our infrastructure systems actually wake up and start talking back to us. And it's not that far away as we start implementing things. And it's going to be disruptive, right? You know, we thought there was a really big disruption when we went from hand drafting to CAD, right? How many people remember that? I mean, there were businesses that went out of business literally because they started billing per hour and didn't realize that they could do it in a quarter of the time. Not good. But, you know, and we took another step when we started being able to design not just the intersection or a simple road, but the entire transit system, right? And now we're able to optimize this. But this era of connection is going to bring in a lot more firepower and a lot more change for every business. Doesn't matter whether you're a financier, an engineer, a contractor, and it's coming. You can say, well, I'm going to bury my head in the sand. It doesn't matter. It's still coming. And there's companies around the world that are going to do this, as you saw with the example in the Netherlands or the example you just saw in Rio Tinto mine or LA, right? These are capabilities that exist, and we can either use them internally to the US or externally or both. And it's not just a technology push, right? Go back to the original quote. You've got to understand where do we want to grow as a city and then use the technology to help get you there. Because the reality computing tied with a in-context model will give you this simulation and visualization capability. The business side is, guess what? Complexity and uniqueness, which used to be a cost premium when you build things, is not that case anymore, right? A 10-person firm has the same IT horsepower as a ENR 50 firm. Right? They don't have the 1,500, nothing against Cora, right? They don't need their own internal server farms. They don't need a big, massive IT staff. They can rent the Amazon cloud for a fraction of the cost and compete and build the same models that the biggest firms can. And if you don't think that's going to flip over the ability to compete, you might want to think about it. So here's a couple more examples, and if you guys could click the lower right corner there on the screen. Here's a couple examples of projects that I did just for fun. This is a lighthouse in Maine. I literally flew that with a friend of mine, captured the photogrammetry, uploaded it in the parking lot, drove home. It's a couple hours away. By the time I got home, I had an email in my inbox that says your model's done, and I download it, and you get the lower right, or lower left. 2 hours processing time. The one on the right, same idea, except this is my town library. Except this was a shorter drive. This is 2 miles, so I had to wait another 45 minutes. But the point being is when you did this, a bunch of photogrammetry just from a drone, and when you measure against, because I'm a surveyor, I surveyed a couple points out there, it was within 3 inches, and it was only 70 photographs in an hour, right? So you can get much tighter detail with more photographs, et cetera, but the whole point is that we now can rapidly model this, and it's not hard anymore because we have the processing power, we have the ability to connect. It's going to change the way we team on projects, and it's going to have a big impact on capital because it should get more efficient. If you guys could kick the upper left and the lower right, So if we can model cities very accurately, and we have the ability to do computational fluid dynamics, which now can be part of engineering, and run bridge scouring programs, every engineer who does any design can now understand the impact at any point in time. You don't have to have a PhD to do these things anymore and run a bunch of calculations and hit or miss. The engineers and the designers have real models of cities, so the water's going to behave just like it would, and you can actually start figuring out, is this a good design or is it not? Right? This is the power of what we want to do. 3D printing was so yesterday. Only because, 3D printing is really just 2.5D, right? You go back and forth 1,000 times. This uses light, electricity, and as you saw, as it popped out, no drippage. It came out of a set of polymer-type material that's smart and intelligent with nanos. It reacts to a certain command, and it creates that helix in a few minutes, right? So it's different when we can start scaling this thing up. And the question is, where do you get your source? Okay, this is kind of a cool thing. And I'm using this as an example of being able to distance, is the fact that giving the models, you can scan them, you can print them in 3D, and that could as well as be in a building or a part. But any idea what that thing looks like, where it's from? I'll give you a hint. Is that better? Right? Now, I'm using extreme distance just because there's always some, well, we work on the other side of the world. Great. Well, you can beam stuff from Mars because it's scanned and then print it out in 3D and physically hold it within a few hours once it gets to arrive, right? So we can start thinking about passing information over massive distances very rapidly, downloading them and using them and sending them back, right? So start thinking about how we want to apply this to infrastructure. Another great thing from the Netherlands. See, these guys left, and I had 2 of them. These people are actually presenting today at the conference. I was in San Francisco last night, but this is MX3D. Essentially what they're doing is they're fabricating bridges and using robots to construct it autonomously, right? When you look at this type of information, and you notice that bridge looks a lot different than what you would normally would have. It's probably nothing like one of Michael's bridges in New York City, right? Why? Because it's using generative design. In other words, you're putting in the parameters. I need a bridge to carry this amount of weight. It's got to have this type of tensile strength. It's got to resist these types of forces. And I want the minimum amount of material possible. And here is the material we want to use. And generative design will run tens of thousands of calculations to create a structure. If that was steel, it would look differently. If that was carbon fiber, the lattices would look differently. He knows the material and then can create the bridge, and this thing can go construct it, right? And there's a reason why it looks really organic, right? That looks like a human bone. Did you ever zoom in on a human bone? Why? Because, hey, we've had, a couple 100,000 years of evolution. Things can be done that in hours now that doesn't take 100,000 years to do these evolutions. But it's being constructed now, all right? And to, can you hit that upper left corner for me, please? Hopefully this works if there's an internet connection over there. Maybe not. Yeah, and just click right in the middle somewhere of that video, just to speed it up, to show you what this thing looks like. And click it a little more there, yeah, and hit play. There you go. All right, that's what those robots do. On the right is the 3D model. On the left is the actual machine, and it just extrudes this stuff out and builds it on the fly. Right? Like I said, 3D printing is like so yesterday. But this is the ability that we start manufacturing things. You know, beyond the building you saw in China is how quickly we can now start doing these types of things. Okay, you can kill that, thank you. And here's where it takes another leap forward. I met the CEO of this firm yesterday in California. It's still early firm. What you see is a person whose job it is to think about 3D printing, and the biggest thing we've had a challenge with is the materials, right? Great, it's a little plastic widget. I can give it to my kid. It's not going to hold the bridge up. This guy has invented a carbon-laced polymer that is 6 times the strength of titanium. So what his job is, and that you see the machine, that's the virtual machine that does the design. There's a physical machine that prints it out. His job is to replace every metal part with that polymer because it'll last 10 times longer than any metal part, and it's a hell of a lot stronger. And you think of the impact, motors, pumps, engines, bridge decks, anything, right? Lightweight, 6 times the strength of titanium, and certainly not equal in cost. So what could you do with that type of material, with that type of manufacturing process? How quickly could we put up buildings and infrastructure and replace things, right? This is what exists, right? This is kind of the state of the art. And then we figure out, okay, well, how do we take advantage of this at some point in the future? So, you know, we have everything coming along, programmable matter, right? Take that material, but add nanos in it, and it tell you, given an instruction, it changes its shape, like from a straight line to a squiggle to a box. That exists. We're working on stuff like that, right? So the whole point being is you can give your infrastructure executable commands, and it can do stuff. Now, the whole idea is not to make it too self-learning, so it's, you know, does everything on its own. There should be a human somewhere in that process, but the whole point is we now will be able to take infrastructure, give it a command, and have it change shape, whether that's a culvert, whether it's a pipe, whether that's a building, whatever it may be. You know, walls that can kind of grow up together when there's a flood potential and then sink back down automatically. I mean, the uses are endless of this. But it all comes back to understanding, having the model and being able to deliver it more effectively and knowing what you want to do. Where does it go from here? Good question, wherever you want to take it. So the whole point here, try to get us back on time, that the inputs are coming from many areas. You know, the media and entertainment, from the powerful visualizations applied to engineeringly accurate centimeter grade, millimeter grade data capture. Fabrication that we have, you know, is really getting more like automotive as we get into this, especially when we get into the robots. We can model entire cities rapidly to get very accurate results. And as George said earlier, to his point, once you have the information, we do great things with it. But the other thing it finds is it tells you where you don't have any information. There's a black hole, and that makes some people nervous. Hey, what's this big hole? That's where all utilities are. Yep. Might want to look at that. Right? So. And of course, you know, movies and entertainment to give the power there. So, I mean, at the end of the day, when we start thinking about the future of our cities and the future of our infrastructure, I go back to the same point. The role of technology is going to be central, but it's got to be combined with a different way of how we want to plan these societies, plan the cities, and make the cities actionable, and build them and not take 200 years to rebuild what we have today, because guess what? It's going to change by tomorrow, and the day after, and the day after. So hopefully that gives you some food for thought. I just put this up because it's kind of fun. I hate to date myself, but anyways, you know, 30 years ago, total stations and a laptop were cool in the field. That was state of the art. 10 years ago, running GPS and scanning, that was state of the art. And now we got drones capturing all that stuff in half the time. when you're certified to fly your drone carefully and with the regulations and know your airspace, by the way. So don't just go out there and wing it. So thank you.
Are there any questions for Terry? We've got time for 1 or 2 questions. Please.
Terry, that was a great presentation. John with eBuilder. Down the street from our office in South Florida, there's a company called Magic Leap. I'm just curious if you've heard about it. They've received, billions of dollars in VC. It's very hush-hush, but it's this augmented virtual reality. And I'm curious if you've come across that and how that, I don't even know much about it, but just from what I've seen, people said it's brought them to tears. I wonder if that would get integrated into something you're doing, if you know much about that at all.
Oh, absolutely. I mean, and for those that don't get it, there's 2 things that are really interesting. There's the virtual reality. That's the ones like the Oculus things where you look like you're looking in a box and you can't see anything around you. And then there's the augmented reality, which is kind of a hybrid. I think these things are developing quickly. The question is going to be is how fast will the augmented reality develop so it makes the virtual reality irrelevant. I'll take the example. Imagine a fighter pilot, right? He's got a helmet, he put down 2 screens. At some point, there's going to be a helmet that brings down a dark screen and it acts totally VR. So you look around, you're in a closed environment, and then you flip it up and bring down the other screen and it's your AR, right? Which you're looking at the physical world, but you can see the things that are going to be there at some point, right? You need to do both. But I think the augmented reality just allows you to have a perception of what's going to be there. And that could, whether that's doing inspections, whether that's once you build the asset and you've scanned it to figure out all the stuff you hid behind the wall that you forgot about, there's massive amounts of things. Because if we can scan and capture it as you're constructing it, and it doesn't matter what you put on the facade, you'll know where everything is, to millimeters. And it's always the thing behind the wall that you got to get to that you don't exactly, is it that, and you got paper plans, the drill. But yeah, no, absolutely. I think the virtual reality is going to have a limit because it kind of makes people sick and it's very enclosed and it's very purpose-built. But the augmented reality will allow you to walk through a building free, not tethered to a computer. And it will be able to wirelessly bring the information from your servers, just like you get something off your BlackBerry or iPhone, and then be able to load these models on demand based on your spatial location. That's when it gets really cool. So there's absolutely a lot coming that way.
Another question right here. Hold on, Chris.
Well, thank you very much, Terry. Mine is kind of contribution or a request for more explanation on this infrastructure. Looking at the presentation you made and the global infrastructure outlook, yes, this is a disquisition, an explanation of what is ongoing in America and most parts of Europe. Now, to assume the proper globalization effect of this improved technology in civil engineering construction, the expansion has to go global. Okay, the focus now should be in places like Africa. Earlier presentations that have been made showed top 10 countries where advancement has gone and top 10 countries that require advancement. Your presentation, yes, has really shown how far the technology has developed in this part of the world. But the focus is should be more in Africa. And what aspect of development and technology you've brought into those areas? But I think that places like Africa and Nigeria, with the kind of population that we have, the effect, the importance of this advancement in technology as you have presented should be more focused and more geared towards that. Thank you.
Yep, no, I mean, I absolutely agree. I mean, there's no one country that's going to have a monopoly on implementing this, right? It's how many people want to take active and do it, right? I mean, a number of years ago, there's many countries in Latin America decided they wanted to be state-of-the-art, right? They didn't follow the U.S. example and put up 75 years of telephone lines up and down mountains. They just went cellular and just skipped over the whole thing. So we're going to see a lot of this leapfrogging, either in different cities, if some of the smart cities really want to take it. or some of the countries that want to do it, right? So these are examples from all around the world. The Netherlands, very small country, very minute. China, very cumbersome, big, but can do things very rapidly. So it all exists. The question is which one country is really going to want to rethink their infrastructure and then take advantage of what exists and make it happen. So, absolutely, nothing stopping. Thanks.
Okay, now, Chris, you can clap.